Okay, so what I'm going to talk next is going to be optional, but I think I would like to cover it in a short time because we actually covered it a little bit. So if you don't want to hang out, you can drop off. If you want to watch it on your own, you can watch it on your own. But this is not going to be material that we cover in exam. But for people who are interested to learn about this, I'm going to cover it because next time we're going to start with virtual memory. So multi-core issues in caching. I think this is very interesting. As you know, all systems today are multi-core systems, and caches are even more important than multi-core system. And I'm going to flash you the pictures that I showed you earlier. I mean, these are all multi-core systems, for example, and multi-core, multi-threaded systems. For example, you have 120 to 128 threads in this case, for example, accessing many caches, right? And that's true for GPUs also, right? So basically, cache efficiency becomes even more important in a multi-core system and a multi-threaded system. Why? Memory bandwidth is at premium. Cache space is a limited resource across many cores and threads. Right? Then the question becomes, how do you design the caches in a multi-core system? This becomes even more interesting in a multi-core system, basically. And many more design decisions come into play. Do you make the caches shared across threads, shared across cores, or do you keep them private to threads or cores? This is similar to the, do you make the caches shared between instructions and data, or do you keep them private to instructions and private to data? Very similar design decision, basically, except it happens to be across threads and cores. How do you maximize the performance of the entire system? And this takes into account the miss rates, of course, but the missed latencies and costs that I mentioned earlier as well. How do you provide quality of service to different threads in a shared cache? If you decide that the cache is going to be shared across threads, how do you guarantee some predictable performance to different threads? And this becomes important because some threads may be very latency sensitive, right? It may be actually responding to some user input. User wants quick decision from that thread. And if it misses in the cache many, many times because some other thread is interfering with that thread in the cache, too bad, right? Should cache management algorithms be aware of threads? That's an important question. How should cache space be allocated to threads in a shared cache? Today, actually, people have finally moved to allocating space in a shared cache to different threads so that they can provide quality of service. Then the question becomes, how should the cache space be allocated? How much cache space be allocated to different threads so that they can satisfy their quality of service, predictability, responsiveness requirements? Many, many interesting questions. And then there's another interesting dimension. Since efficiency is so important, should we maybe start considering storing data in a compressed format in some of the caches so that we can actually make better use of the space that we have? Of course, there are downsides to it. Now, whenever you access the cache, you need to compress the data, right? Unless you're operating on compressed data in your processor core, which is not the case today, of course, right? And then how do you do better use prediction and management in caches? Because this is much more important in a multi-core system because you have many, many more threads requiring service from the memory hierarchy. Okay, so a private versus shared cache, as I said, this is very similar to instruction versus data. In a private cache, cache belongs to one core or one thread. In a shared cache, cache is shared by multiple cores. So this is the picture, if you will. This is a very simple picture, right? At the core granularity, these L2 caches are private. At the core granularity, this L2 cache is shared. So if the cache belongs to one core, a shared block may be in multiple caches, of course, right? So you have a redundancy problem. Whereas if the cache is shared across many cores, a single memory block occupies only one location, right? That's one advantage of a shared cache for you immediately. But it's a trade-off. Like everything, it's a trade-off. Resource sharing concept is actually a bigger concept. Basically, instead of dedicating a hardware resource to a hardware context or a core or a thread, hardware context can be loosely thought of as a core or thread, allow multiple hardware contexts to use it. In this case, the resource happens to be the L2 cache. In this case, basically, we're dedicating the L2 cache to one core. Whereas here, we're sharing the L2 cache across multiple cores, right? Example resource can be many, though. It could be functional units, pipeline, caches, buses, memory, SSDs. Imagine anything in the system. So why do we want to do resource sharing? Because it improves utilization and efficiency. As a result, it leads to higher throughput. Why? Because when a resource is not used by one thread, another thread can use it, right? If they share the resource. If the resource is partitioned, that resource is private, even if this thread is not using its private resource, another thread cannot use it because it's private to that thread, right? You've dedicated the resource to that thread. So by definition, resource sharing provides better utilization and efficiency, which leads to higher throughput overall. And also, there's no need to replicate the shared data, which also leads to higher throughput, because if all threads are using the same data, let's say, then all of that data is replicated in different caches, and you need to bring the data to different caches one by one, right? Whereas if you have a shared cache, you didn't replicate the data inside that cache because it's a shared cache by definition, right? Okay, so resource sharing also reduces communication latency. For example, if you have data shared between multiple threads, that can be kept in the same cache in multi-threaded processors, right? That's nice, of course. And finally, this is compatible with the shared memory programming model. Probably you're seeing the shared memory programming model in your parallel programming course. And if you're sharing the memory, it makes sense to share the memory resources, physical resources as well. But of course, resource sharing also comes with disadvantages. It results in contention for resources. And we saw this, if you remember, in earlier lectures. In one of the mysteries, we talked about memory performance attacks, right? This happened because different threads, different applications shared the memory bus and the memory banks and the memory row buffer. As a result, the scheduler became a contended resource. And if the decisions made by the scheduler are not good enough, then you have significant unfairness in the system. So basically, contention for resources, when the resource is not idle because one thread is utilizing it, another thread cannot use it. By definition, you don't have a private resource for yourself. So you cannot have guaranteed service in that resource, essentially. So if this happens in time and space, in time, when the resource is not idle, another thread cannot use it. If the space is occupied by one thread, another thread needs to reoccupy it. So essentially, one thread can evict the cache block of another thread, essentially. And this may happen, for example, if you have a shared 32 kilobyte cache and each thread needs 32 kilobyte on its own, too bad. You may be thrashing the cache, right? So basically, disadvantage of resource sharing is it can sometimes reduce each thread's performance or some threads' performance or all threads' performance, actually. Thread performance can be worse than when it's run alone. So because when you're running alone on the same system, you have the cache to yourself. But when you're running together with multiple threads, you don't have the cache to yourself. As a result, you may actually lose performance significantly because some other thread is evicting your cache blocks, right? So this is a big problem with resource sharing in general. So you need to somehow control the resource sharing if you don't want to run into issues like this. And we talked about this in one of the mysteries lectures from the perspective of the memory controller. Similar ideas can be applied to caches. Actually, some of you mentioned at that time, caches may have the same problem. And absolutely, yes. Okay, so if you share the resources, you're eliminating performance isolation because the resources are not private anymore. As a result, the thread that's executing is not guaranteed some amount of cache, for example, or some amount of memory bandwidth. As a result, it's always its performance is always dependent on what else the other threads running in the system is doing to its blocks in the cache, right? How much interference there is from the other threads. As a result, you may get inconsistent performance across different runs of the same program. And that's potentially a downside because you may want to optimize your program for the cache hierarchy, right? If you cannot assume that your cache hierarchy is dedicated to you, then it's very hard to optimize the performance of your program because somebody else is interfering with you, and that somebody else may be different every time, right? Performance isolation is important for performance optimization of the programs. That's why also knowing how much cache you may have in a system is important so that you can optimize the performance. Basically, thread performance depends on co-executing threads, and that makes performance isolation go away, and performance optimization becomes extremely difficult, if not impossible. And uncontrolled resource sharing, if you don't control the resource sharing, as we have seen in memory performance attacks, for example, this degrades quality of service, it degrades predictability in the system, and basically you have an unpredictable and potentially vulnerable system to denial of service attacks as well. It's because you cause unfairness and starvation to some threads. So basically, resource sharing is good for throughput, but you need to be careful about not causing these disadvantages as well. You need to efficiently and fairly utilize the shared resources in a system so that you don't run into these bad disadvantages that we have discussed earlier in memory performance attacks as well. So private versus shared cache is one example of this, basically. In a private cache, resource is not shared. In a shared cache, the resource is shared. And clearly you have the same issues. So let's take a look at this particular example. If we're looking at the advantages of shared caches between cores over private caches between cores. And we're going to also look at the disadvantages. So clearly, if you have shared cache, you have high effective capacity. If one core is not using the 4 megabyte L2 cache that's dedicated to it, another core can use that resource. Similar to the example that I gave you between instruction and data caches, right? You can dynamically allocate the resources. And this could be actually very good, right? Imagine 4 L2 caches, each of them 4 megabytes. So effective capacity is 16 megabytes. If you make them partitioned across 4 cores, each core gets 4 megabytes. That's great. But if one core needs 8 megabytes, it basically thrashes its own cache. It cannot use the cache space dedicated to other cores. But if you do the sharing of the cache capacity, then you get high effective capacity. And this is very similar to, basically, this is enabled by dynamic partitioning of the available cache space. You don't get fragmentation issues due to static partitioning, which is essentially what I talked about. If one core does not utilize some space, another core can. And that sounds great. And also, it's easier to maintain coherence because a cache block is in a single location. The cache block is not replicated across different caches, which requires maintaining coherence. If the cache block is in a single location, that's it. You don't need to keep it coherent, at least at that level of the cache, right? Disadvantage, of course, there's disadvantages, right? And it's slower access because cache is not tightly coupled with the core. If you have a cache private to the core, you can tightly couple the cache to the core. In fact, you can integrate it to the design of the core also better, even if it's an L2 cache, for example. So you can make it faster access for that core. But now if you have a shared cache, you need to have some sort of interconnect connecting the cores and the cache. As a result, by nature, it has to be slower. And of course, as we talked, cores incur conflict misses due to other cores' accesses. These are misses due to inter-core interference. And some cores can destroy the hit rate of other cores essentially this way. So imagine one core having good locality in its cache. Imagine another core streaming through terabytes of memory. And it's bringing all of that data into the cache and evicting the core that has good locality in the cache. So that sounds like a bad thing, and it should not happen. And of course, guaranteeing a minimum level of service or fairness to each thread or each core is harder now. How much space do you allocate to each core? How much bandwidth do you allocate? How do you design a partitionable cache? And these are all good questions to ask. And clearly, these questions arise in real system designs, real multi-core system designs, because real multi-core system designs have both private caches as well as shared caches. And we've seen examples of this. I'm going to show you maybe more examples. I don't remember if they were in these slides, but maybe in the beginning of the next lecture, I will show you. But certainly, private caches, L1 caches are private to the core, but they may be shared across multiple threads within the same core, because each core actually does either fine-grained multi-threading or simultaneous multi-threading, which we have discussed earlier. You have multiple threads, hardware context inside a core. L1 caches are usually private to the core, but shared between multiple threads that are multiple hardware contexts within the core. L2 caches may or may not be private to the core. L3 caches are usually shared across cores and maybe many, many cores in the system. So these issues arise in existing systems, and existing systems actually have to make choices. So this is an issue that happens in multi-core systems that is very, very important to handle. It affects your performance a lot, actually. So if you're interested in this, clearly there's a lot more to talk about. We didn't even talk about mechanisms to get the benefits of both shared and private at the same time, for example. But if you're interested, you can take lectures. You can either take the advanced course, or you can watch some lectures online that we put up. And there are also software-based management mechanisms. Page coloring, for example, that's depicted in this slide, is a software-based cache partitioning mechanism. And the software can allocate pages to different indices in the cache such that different applications do not conflict with each other in the cache. And this is a beautiful idea that is employed in some operating systems, and it can actually enable you to manage your cache better at the software level. But of course, it has its downsides as well, because at the software level, you don't have a lot of control on your cache. So you may actually, whenever you need to reconfigure the partitions of your cache, you may actually incur a lot of performance loss in this case. But these are very, very interesting ideas. They're software ideas, they're hardware ideas, they're software-hardware cooperative ideas to manage the caches and the cache hierarchy in the multi-core systems as well. And there's a lot more to be done in this area. And of course, there are approaches to reuse prediction that may better manage the caches. Using better compressed cache hierarchies are an example of also a better, more efficiently utilizing the cache hierarchy. And there's a lot more ideas here that I'm not going to cover, but I'm going to refer you to these lectures over here. And also there are a lot of ideas on memory resource management as well, which we didn't have a lot of time to talk about, but we mentioned, for example, memory performance attacks. And there are a lot of interesting questions over here, like how do we reduce the inter-thread interference? How do we control it? And how do we make the memory system more configurable, flexible, such that it can cater to different needs and different access patterns of different applications? And again, there's a lot more to talk about over here, but we don't have time in this particular lecture. Okay, maybe I will, again, all of this is optional. I will quickly cover cache coherence as well, and then we'll be done, because I'm not going to actually talk more about it, but probably you've seen cache coherence in your parallel programming lectures if you're still hanging out in the lecture. But the basic idea of cache coherence is if you have multiple processors, and if multiple processors cache the same block, how do they ensure they all see a consistent state? That's the basic idea over here. And you've probably seen it in your parallel programming lectures. That's why we're not going to spend a lot of time, but you may not have seen how it's implemented in hardware, for example. And that's we're not going to cover also in this lecture. For that, you need to take an advanced course. But basically, the problem looks like this. You have two processors in this particular case, and you have two caches, and you have one memory location, X, that stores 1000. Let's say processor 2 loads into R2, 1000, this location X, and that load gets loaded into the cache. And then processor 1 later loads also into one of its registers, location X, that gets loaded into processor 1's cache. Now, both of the processors have these two, the same location redundantly stored in their caches, because these are private caches. They're not shared caches. Now you see the benefit of a shared cache. Shared cache doesn't have this problem, right? And then let's say processor 1 does something, increments or increases the value to 2000 and stores the result into its cache. Now the values are inconsistent. The value of X is seen by processor 1 as 2000. It's seen by processor 2 as 1000. So whenever processor 1 modifies the location, processor 2 should not load 1000 from its cache, because somebody else updated that location in between. And this is really required so that you can guarantee consistency in a system, which is a broader topic that I will refer you to later on. But if processor 2 loads 1000, in this case, your synchronization primitives may not be correctly implemented in hardware. As a result, you may not be able to synchronize between these processors correctly. And that's why you need to keep the caches coherent with each other. Whenever processor 1 updates this value, maybe that update gets propagated over here, or maybe you invalidate the same location X from all of the other caches. There are multiple approaches to coherence, which I'm not going to talk about right now, but you can certainly approach the problem as updating also other processors' locations, other caches that cache the same data. So whenever you update this cache, you update all of the other caches as well. This is called an update-based protocol. Or whenever you update this cache, you may decide to invalidate all of the other locations. And of course, there's a question, what happens to main memory as well, right? Do you update the main memory as well? But I'm not going to talk about those in detail. I'm going to give you one example cache coherence protocol, and then we're going to end with pointers to other lectures. Essentially, this is a very simple coherence scheme. This is an invalidation-based coherence scheme. All caches snoop, observe each other's read and write operations. All operations done by each processor is exposed to all of the caches. Assume that this is implementable. This could be implemented in a bus-based system. Basically, everybody is connected to the same bus, same single wire, let's say. And snooping is basically looking at what's on the wire. And whenever a processor writes a block or reads a block, they basically broadcast it to everyone. And if a processor writes to a block, all other caches that have the same block in their cache invalidate the block. That's the idea of this protocol. And this is a very simple two-state protocol. A cache block can be in valid and invalid state. And let's assume that it's in the valid state. When you observe a write on the bus, each cache basically snoops the bus, or observes what other processors are doing. Whenever you observe that somebody else is writing to this particular block, you invalidate the block. That's the idea. And that's basically what this says. I'm not going to go into the details of this, but there are some assumptions for why and when and under what conditions this protocol works. For example, the caches need to be write through because of the way signals are defined over here. It has to be no write allocate because of the way, again, signals are defined over here. And the local processor can do a read or write to the block. As you can see, local processors potentially doing read or write to the block. And whenever some other processor does a read or write to the block, that gets broadcast on the bus so that every other processor can execute the state machine for that given block. Okay, if the block is valid in the cache, and if there's a bus write to a block, meaning that some other processor is writing to that block, each cache independently transitions to the invalid state. They invalidate the block. Okay, so this is a very simple protocol. Existing systems do not use it because it has a lot of disadvantages, but we're not going to go into it. Existing systems actually use more states. And if you're really interested in this, this is one example of a MESI protocol, for example, which was developed in the 1980s, which a variant of which is used in many existing processors today. But again, I'm not going to go into the details of it. You may have seen examples of it in the parallel programming course, but how it's implemented, why it works, what are the design decisions that can make it better, that is the subject of a future course. And if you're interested, you can certainly watch the lecture early on as well, because now you have the basics to watch the lecture. And there's also an important distinction between coherence and consistency. Memory ordering becomes an important problem for synchronization as well. And we cover those issues in advanced lectures. I just wanted to give you the name consistency or memory ordering. How do you do the memory ordering across different blocks? And how does the processor observe the memory ordering across different blocks becomes important, extremely important for correct synchronization across processors. And you need to provide some primitives inside the hardware so that the programmer can synchronize different processes correctly that are executing on different cores or different multiprocessors. But sequential consistency is one example. And this slide, this particular slide is describing sequential consistency, for example. But again, you don't need to know about any of this. All of this part of the lecture that talks about multi-core issues in caching was optional, as I said. But if you're interested, there's a lot of interesting stuff to learn about over here. And these are also very interesting research topics going into the future in terms of that span both hardware and the software, and critically thinking about existing approaches and how to make them better can enable much more scalable systems into the future. So these are the list of lectures on cache coherence and consistency. And this is the place that I'm going to stop. I think in the next lecture, we will pick up with prefetching. I think this is an important concept that I would like everybody to learn about. And then we're going to move into virtual memory. So unless I see there are still some people following, that's great. But again, if you were not following the last 25 minutes or so, they were all optional. But if you have any burning questions, I'm happy to take them. Otherwise, this is probably a good place to hang up and wish you a great weekend. Okay, I don't see any questions. So have a great weekend. I will see you next Thursday when we will talk about prefetching and virtual memory. Take care and stay safe. And hopefully get vaccinated, because that's happening. And hopefully with everyone vaccinated, we'll have a healthy next semester that's going to be much better than this semester. Okay, take care.